your forehead for this class, this would be the thing to tattoo to your forehead.
But then you can't see it.
You're allowed, mirrors are totally allowed on this exam.
But wouldn't it be easier to like touch it with your hand or something?
I put it to my forearm as well.
That would be cheating.
Wait, it was on my forearm as well the last time.
It was on your forearm or something?
I had it on my forehead and my forearm.
Yeah, but it was backwards on your... Oh, wait, was it backwards on your forehead?
You could read it.
I can read it, oh yeah. Make sure if you tattoo it on your forehead and you're going to look at it in a mirror, that it is backwards. So that when you look at it in the mirror, it looks like it's forwards. Or it's a mirror. You get what I'm saying. Okay, so the next thing is we need to transition our way into circuits, right? And this chapter starts doing that. Remember, we're still on chapter 29. It was a long chapter. Now, potential. The origins for potential are really from what? If I was like, here, make a potential, what would you do? You separate charges. So potential comes by charge separation. And there's a lot of devices to do it. On the very first day of lab, remember what we used? Van de Graaff. AFF, I don't remember. 2 A's, 2 F's? I don't know. Anyway, Van de Graaff generator, right? That's exactly what that does. It pulls a whole bunch. That looks like a penis.
Nah, not at all.
It pulls a whole bunch of charge into the head. Anyway, it separates charge, right? It takes up. Sorry, I did not mean to do that. I don't even have one drawn in my notes, but it turned out to be a bad drawing.
That was
Sorry.
very strong.
Anyway, it pulls a bunch of charges and separates them by pulling some to the top part, whether they be positive or negative, and that creates a potential difference. Okay? A better potential. Sorry. A better device for creating charge separation is a battery. Now, a battery is like a charge escalator. Okay? It uses chemical reactions, and the specifics are obscured in the depths of chemistry. But it uses some chemical reactions that lift charge up this escalator. Okay? In other words, it creates some constant charge separation, which causes there to be a voltage across this battery. V bat, which we also call the EMF, or E, like that, as it is often used. Okay, now what causes this? Well, it's ion flow. So whatever is happening in the battery, there's some ions that go in solution. They go from one side of the battery to the other side of the battery, driven by some chemical reaction, and that causes an abundance of charges to build up over here. So we have a bunch of positive charges here, and we have negative charges on the bottom. Now, after the battery has got as much charge as you need on the top and bottom as to provide V bat, the chemical reaction basically stops until you connect this battery to a circuit, and then some of this charge leaps onto the wire, goes around, does your bidding, and then comes back. Well, in that case, the battery needs to replenish this positive charge that it lost. Well, it does that through starting its chemical reaction again and pumping more of these positive charges to the positive terminal again. Okay? So a battery is a sweet thing because it keeps a constant voltage and it replenishes itself through electrochemical means. I'm sorry I drew that penis. I did not mean to do that.
It's only on video.
Oh, that was inappropriate. All right, so now batteries can be added in series like this, and you've probably done this before in your flashlight. except for probably not like this. Well, maybe you've done this and you're like, ah, man, my flashlight is really dim or it doesn't even work. Okay? And when you add batteries in series, let's say this is 3 volts and this is 2 volts and this is 1 volt. Okay, this is the minus side, the plus side, the minus side, the plus side, the plus side, the minus side. Okay, if we want to know the potential across this whole thing, what's the potential going to be?
4.
Yeah, all right, we go from here to here, that goes up plus 3. From here to here, we go up plus 2, so that's 3 plus 2, that's 5. And then we go down here, that's minus 1, right? We're going from positive to negative, that's minus 1, so that gives us 4 volts. In other words, to find the change in voltage or delta V across all these batteries, you just add them all up. So this is delta V1 plus delta V2 plus delta V3, and so on. Okay, so that's how you add up the voltages from a bunch of batteries in series, which is why we put batteries in series in the first place, is because we want to get higher voltages. So you take a whole bunch of 1.5 volt batteries and you add them all together until you get whatever voltage you need. Okay, and this is a sweet thing about batteries. And that's pretty much it about batteries in that chapter. But we did start talking about capacitors in this chapter. Capacitors and batteries, they're a little bit alike in the fact that they can hold charge and they can discharge, but a battery will replenish its charge continuously through chemical reaction, and a capacitor simply stores charge. Okay, so if you have a capacitor, the main equation you need is something like this: Q equals C times delta V. Okay, that's the capacitance equation. C, that's the capacitance right there. That is what determines the capacitance of a capacitor. The geometric properties, right? It's cross-sectional, or it's the area of the two plates, and it has to do with the distance between the two plates and stuff like that, right? So that's a strictly geometric constraint. It also actually has to do with the material that's inside. It's called a dielectric. I won't ask you anything about dielectrics on the exam, but you can put some dielectric in there, and that will increase the capacitance. Anyway, Q is the amount of charge on the capacitor, and delta V, that is the voltage across the capacitor. So if this is a capacitor right here, you have some voltage across it, that's delta V. You have some amount of charge that is accumulated on it, like that. That is Q, and then the capacitance is given by C, and this has the relationship between all three of those values. Where does a capacitor store the energy, by the way? It's in the electric field. Okay, and also capacitors in parallel. Okay, remember, capacitors, they're like the reverse of resistors. Okay, so capacitors in parallel, that's the pain in the butt one for resistors, because it's 1 over the resistors in, you know what I'm saying. But capacitors in parallel, they're just going to be the equivalent capacitance. C equivalent is equal to C1 plus C2 plus C3, and so on. Okay, that's when capacitors look something like this. Like this. Okay, we have some potential across these capacitors, and if we have capacitor C1, C2, and C3 to get the equivalent capacitance, you just add them up. And that makes sense, right? This kind of looks like it's a big, long, extended capacitor. Okay? If you were to just extend the area of one capacitor, well, it would just extend over in this direction, right? In fact, if we wanted to make a big capacitor, it might look something like this, just extend all the way across, and that would be a way to make a big capacitor. So that's how I always think of capacitors in parallel. it just kind of makes one big capacitor. Now, what do capacitors in parallel share?
Voltage.
Voltage, okay? So capacitors in parallel share voltage. So if this is 10 volts and this is maybe 5 volts, okay? Well, that means that each one of these is going to have 5 volts across it. 10 minus 5 is 5, and they're all going to have that same 5 volts across them. That's what capacitors in parallel share. Capacitors in series, they're the more pain in the butt ones. So and they might look something like this. Let's say we have some battery, maybe like that, okay? And then we have a bunch of capacitors of different size, maybe, all in a row. This is minus, this is plus, C1, C2, and C3. For this, you have to take 1 over the equivalent capacitance is equal to 1 over C1 plus 1 over C2 plus 1 over C3, and so on. Okay, so you add the inverse of all the capacitances up, and then you take the inverse of that to find the equivalent capacitance. Now, what do all capacitors in series share? Charge, right? So caps in series share charge. Well, let's think about that. That means, let's say like we have some voltage across here, and that means we have a voltage across this whole thing right there. Well, what that's going to do is it's going to cause a bunch of charges to collect on this plate. That means an equivalent number of negative charges collect on that plate. That's what capacitors do. Well, in that case, where do these negative charges come from? Where do they have to come from? Yeah, C2, right? These positive charges, this whole little section of wire right here and plates, it's all neutral to begin with. These negative charges, they can't come from nowhere. They have to come from this plate right here, which leaves a bunch of positive charges there. Just the same number as you have negative charges there, which is just going to be the same number of positive charges there, and then the cycle continues. Now we're going to have a bunch of negative charges collected there, a bunch of positive charges collected there, a bunch of negative charges collected there, and the charge is the same. So caps in series share charge, caps in parallel share voltage, and you're going to need to use that to do these circuits. One other thing is that the energy in a capacitor U sub C, that's the energy of a capacitor, that's equal to 1/2 times C times delta V squared, which looks an awful lot like the spring equation. Interesting. Anyway, it's also equal to epsilon naught over 2 times AD times E squared. So if you have some potential, some change in potential, and if you have some electric field, you can find the energy stored in the capacitor. Yes?
Yeah, so what happens with capacitors in series and voltage?
With voltage,
Do they share it?
there's no relationship between with voltage and capacitors. There would just be, what you would have to do is you would have to say, okay, well, we know that, for instance, right, if this was like 12 volts and this is 0 volts, we know that 12 volts drops across here, okay? What we could do is find the equivalent capacitance, find the charge across the equivalent capacitance. So you basically turn this into one circuit that looks like this, where this has CEQ, right? The equivalent capacitance, using that right there. Now we can use Q equals C times delta V. We know delta V across this is how many volts? 12 volts. So we can calculate the amount of charge on it. We then can say, okay, well now that we know the charge on this guy, that's the same as the charge on this guy. So we find Q here, okay? That means this is also going to have Q, and that's going to have Q, and that's going to have Q. So now that we know Q, and we know the capacitance of each one of those, we can use this backwards to find out what the change in voltage is across each one of those. So you use the you use the charge then to find the voltage. So you got to kind of work backwards. Yeah. And we did one of these in class where we had some circuit that looked like this. I'm not going to do it, but if you want to talk about it, I mean, this would be an example. So here we have some battery, I think it was 12 volts. And then we had C1 was equal to 3 microfarads. C2 was equal to 1 microfarad. And C3 was equal to 5 microfarads. And I wanted you to find the charge and the voltage across each one of these capacitors. Well, what you do is you break it down. These two are in parallel, so you find the equivalent capacitance of those two. Then this equivalent capacitor and that capacitor are in series. You add those together using the series equations, and you get one circuit with one capacitance just like this. You then use Q equals C times delta V to find, the charge across it, and then you start working your way back. If you know that the charge across that one equivalent capacitor, you then break it up into the two series capacitors, and they're going to share charge, and then you break it up again into these parallel capacitors and work your way backwards. I'm not going to do one right now, but we did one in class, and if you want some help with any of those, come and see me in my office hour tomorrow, and we can talk about it more. But